Okay, so we're now going to move into a type of problem that is definitely a Newton's first law application. Again, so in Newton's first law, F net is always zero because the object is not accelerating, right? Or rather, I should say the object's not accelerating because F net is zero, okay? So when we have, for example, well, this goes for any object, okay, but we're going to look at hanging sign questions. If you're ever looking at an object and it's not accelerating, okay, maybe it's moving, but it's not accelerating, okay, then it is all of the net forces acting, all the forces acting on it add up to zero, right? So looking at this sign, if you see a sign hanging anywhere, shouldn't be accelerating, right? Unless maybe it's blowing in the wind, but these ones are not, okay? So looking at this, we know that all forces acting on it must add up to zero. So the sign's mass is 250 kilograms. Okay, they started our representational diagram, but let's add our forces to it. So first of all, it has mass. If it has mass, what force does it feel? Automatically, it's going to feel gravity, right? And just a reminder, Fg is always mg. Okay, if you have something's mass, you know its weight, assuming we're on Earth. Okay, great. Okay, now what's this thing, this cable here connecting it to the wall? What kind of force is that going to provide? Well, that would provide some tension force up along that angle. Okay, now we know this sign isn't accelerating. So looking at those two forces I've drawn, am I done? Right, I have this thing down, okay, and maybe this cancels out the downness, but now it has some leftness, right? It's got an x component to the left. So I must be missing a force. If you know an object's not accelerating, and when you add them all up, you don't get zero, something's going on, okay? And that's because of this bar here, right? So this bar is actually going to provide a normal force, okay? Or you can think of it as the wall is going to provide a normal force to the bar, which is going to provide a normal force to the sign, right? So a normal force, just a kind of a pushing normal force. And there we go. Now we have the upness of the tension to cancel with the downness of the gravity. We have the rightness of the normal force to cancel with the leftness of the tension force. Okay, so let's simplify this down to a, that's probably have to be a bit bigger to actually look like it cancels. Let's draw our free body diagram. Okay, so we simplify the sign down to just a point representing its mass. Okay, and so the normal force is off to the right. Right? The tension force goes just as far left, we know, because it has to cancel out. There can't be a net force in the x or the y if there's going to be no overall net force. Just far enough to the left to cancel out that. Okay, the rightness of the normal. And then the gravity must be going down just far enough to cancel out the tension, the upness of the tension. Okay, let's just quickly take a look. What does Ft have if it's on an angle, right? What do all of them have, truthfully? But they have components, right? It's just that Ft doesn't have one of its components being zero. It has an Ftx and it has an Fty, and neither is zero. Okay, and one more thing we know from the picture, we know this angle, that's 30 degrees. Okay, cool. Let's draw our VAD. So whenever we're doing a Newton's first law question, which again, signs are a great example of, okay? Signs are a great example of a Newton's first law question. Where do we have to kind of end up on our VAD? Right back where we started, right? There can't be a net force. So once we add all the vectors up, if we ever end up looking like there's going to be a net force, we mess something up if we know the object's not accelerating, right? So there's our normal force. We know now that our tension needs to cancel with the rightness of the normal force, right? Its leftness must cancel the rightness of the normal force. And then, right, we're saying, okay, we're up here. Is there a net force? No, there's not, because there comes gravity to save the day, right? So overall, if I were to draw the net force vector, I wouldn't draw anything because there is no net force vector, right? From the beginning of the first to the end of the last, there's no space at all going on here, okay? Again, this angle here, right? Because the angle here is 30 degrees between the x and the y axis, right? And Fn is completely in the x, Fg is completely in the y. This angle is actually also 30 degrees. That might be useful later. Okay, to wrap our head around the physics a bit more, let's do a VAD in the x-axis. So what vectors have an x component? Well, again, we have Ftx, right? Ftx goes this way. And we know it's not accelerating. If it's not accelerating at all, it can't be accelerating in the x-axis, that's for sure. So if it's not accelerating in the x-axis, okay, there must be something back that way. I say it like it's a mystery. We know what it is, right? It's the normal force. So that overall, there's no net force in the x-axis. What about in the y-axis? What does that VAD look like? Well, what are the forces with y components? What is the y interesting stuff going on? Well, we have FTY up, okay, and then we have FGY, which is just FG, down. So that overall, there's no net force. So the tension is responsible for fighting the gravity, okay? The normal force is responsible for kind of taking off the x-ness of the tension that has to be introduced because of the angle here. All right, so all of these Newton's first law type questions and all of these sign questions boil down to setting F net x equal to 0, F net y equal to 0, and then solving using that. Or sometimes you only need to work in one, okay? So for example, here, we don't really know much about the normal force, okay? We could figure it out if we figured out the tension, but we do have enough right away to figure out the force of gravity. So I'm actually going to go straight to the y-axis. Okay, I'm going to say, well, in the y-axis, there can't be a net force, right? Because this object is not accelerating. This sign is not accelerating down or accelerating up. Okay, so F net y equals 0. It's a good starting point for anything where you know it's not moving. If F net y is 0, again, always, this is how we get F net y, right? Like we said with our VAD here in the y-axis. F net y is the y component of every force that's working here. So FTY plus FNY, which, yes, I hear you, that's 0. I'm just writing it in to say that I'm considering the y component of every force. It's okay if one of those is 0. Okay, so FTY plus FGY equals 0. The y component of the tension plus gravity. Okay, just changing what is the y component of gravity. It's just gravity. It's all in the y-axis, right? Equals 0. Now we're going to do something here. It's always a good idea while you're manipulating, when something pops up in the math, ask yourself, does that kind of check out with what I know is true? And sorry, I got ahead of myself. I kind of didn't say what we're looking for here. So sorry, what must be the tensile strength of the chain, right? Also, we know that the sign's mass is 250 kilograms. I kind of jumped right in. I got excited. Sorry about that. So we're looking for how strong this chain needs to be to support the sign if the sign is 250 kilograms. Okay, so that's why we're kind of working here on the y-axis. So again, what was I saying? I was saying that when something pops up in the math, ask yourself if that kind of checks out with what you were saying or what you were thinking, right? What are we saying here at this point? This is interesting. We're saying that the y tension, the y component of the tension is equal but opposite, equal but with the opposite sign. So just as big but in the other direction as the gravitational force, right? Well, that makes sense. Why is the tension there anyway? It's to cancel out the gravity, right? It needs to be just as big up as it was down. So opposite direction, but just as large. Okay, great. FTY equals negative FG. How do I get FTY? Well, FTY is opposite to that 30-degree angle there. The hypotenuse that I'm looking for overall is FT, okay? So will I directly get FTY? Maybe not, but now I can bring FT in, and since I can figure out FG, I can actually solve for the FT, which is the point of the question, right? The point of the question is to find the tensile strength of the chain. So let me show you what I mean. So sine of 30 degrees equals opposite over hypotenuse. So equals opposite is FTY over hypotenuse is FT. Now remember, what am I looking for? FT. Okay, so FTY then multiply both sides by FT equals sine of 30 degrees times the tension force, FT. Okay, I'm going to bring that fact down here, and let's just see if we get a little inspired here. So I'm going to bring that fact back down here. FTY is, yes, it's FTY, but we just said it's also sine of 30 degrees times the tension force. The total tension force, which remember is what this whole question is asking us to find, is equal to negative the force of gravity. Okay, so same size as the force of gravity, but in the other direction. Sine of 30 degrees then times Ft equals negative, what is every Fg, every weight? It's mg. Oh my goodness, I know all of this stuff, right? I know m, I know g, acceleration due to gravity, that's negative 9.81. Sine 30, that's just a number. So look at this. I've actually now solved it. I'm going to use divide both sides by sine of 30 degrees. Okay, divide that side by sine of 30 degrees. And we get that the tension force, which again, what we wanted, the tension force is equal to negative mg over sine of 30 degrees. And so that's negative, okay? And sorry, quickly before I go, I'm going to define my directions because I'm throwing in numbers now. I need to be careful with what directions are actually going to mean in terms of signs. So let's call up positive, down negative. Might as well call right positive and left negative, though that's not going to be relevant to this part. Negative, the mass we were told was 250 kilograms, okay? Now, g is 9.81 meters per second squared. It's a vector. It's down, so negative 9.81 meters per second squared, all over the sine of 30 degrees. And if you plug that all into your calculator carefully, you'll get that the force of tension, okay, the minimum tensile strength of the chain for it to be supporting this sine would be 4.91 times 10 to the third power newtons. Okay, by the way, this is the type of calculation that engineers do all the time. Okay, not just engineers, there's all kinds of professions that would do these kinds of calculations with materials to see what kind of materials they can use for any kind of job, whether it's construction or in mining, things like that, right? You need to figure out, is the material you're working with, is its tensile strength large enough to actually finish the job that it is or to perform the task that you're asking it to perform, okay? So whoever hung this sign would have went and said, we got to calculate if this chain is strong enough to do it, okay? Tension, this force of tension is it's a force, so it's a vector, so we really should give it a sign, or the direction, sorry, right? In this case, we would say it's at, if this is 30 degrees, okay, then all the way around would be 180, so that's just 150. Not all the way around, but halfway, I guess. So at 150 degrees. Okay, using Cartesian coordinates there, not cardinal, not compass coordinates. So example 8 here, where we have a sign on a wall. This actually looks a lot like the other one, just mirrored and not quite as steep of an angle. Only 25 degrees here. Okay. So when we calculate, it's asking us here if the chain can hold a maximum of 2.5 times 10 to the 3 newtons, or 2,500 newtons. If that's the maximum tensile strength before the chain would break, what's the heaviest? What's the heaviest, or the maximum? Yeah, the maximum weight of the sign. And what is the minimum strength of the supporting bar? So that's this thing right here. What is the minimum strength of that? Because that's important to consider too. Okay, weight, what is that, right? Yes, we could say W, but for the most part, we actually call it Fg, right? The force of gravity, that is weight, okay? So we need to figure out what is Fg. Before we get too into the math, let's make sure we know what we're talking about in terms of the forces going on here. So how do we do that? We label them. So there's our Fg, always down from the center of mass, okay? Our tension in the strength will be acting that way along the chain, okay? And then what is causing this? Again, as I've drawn it, it looks like it should be accelerating that way, but then we realize, aha, we forgot the normal force from that support bar there. Okay, moving on to a free body diagram. Simplify it all out. Okay, we know it's not accelerating, so any force that's a present must be canceled out by some other force in both axes. So there's our tension force. Okay, what makes the upness of this go away? Well, the downness of gravity. Not quite far enough, I don't think. The downness of gravity. What makes the rightness of the tension go away? Well, the leftness of the normal force. All right, great. Let's just, while we've got it here, kind of separate this so we can see what we mean when we say FTX and FTY, right? Which way is FTX? Well, it's off that way, to the right. That's FTX, the X component of the tension. Which way is FTY? Upward, that way, FTY, okay? and they even told us this angle is 25 degrees. Well, let's draw VAD, vector addition. What do we know about where we have to end up? Right, well, right back where we started, because there can be no net force. So there is the tension. Okay, let's get back down with the gravity. Again, it doesn't matter as long as you draw them tip to tail in a reasonable fashion. It doesn't matter what order you go to, what order you draw them, right? And then which way is the normal force? Aha, good. We are going to end up back at 0 because the normal force is back like that. Just for understanding it a bit better, let's do our x-axis VAD. What's that look like? Well, what has an x component? If we come back to our free body here, we have ftx off this way, but bringing it right back to 0 overall, because if the net force is 0, then the x net force better be 0 as well. So that's ftx, that's fn, okay? And same goes for the y-axis. If overall there's no acceleration, then there better be no acceleration in the y-axis either, which means there better be no net force in the y-axis. So Fty would bring us up, but we don't actually accelerate because remember, Fg is pulling right back down just as hard, okay? All right, let's go out to, we'll do them one at a time. We'll start with A, okay? So A was calculating the maximum sine weight. Now, to do that, if we're looking at weight, if we're looking at gravity, we're probably thinking the y-axis is what we're interested in, right? Or at least eventually that's what we'll be interested in. So let's start there and see how it goes. So for A, we'll start by analyzing the y-axis. Okay, so A, what do we know about the net force in the y-axis? Well, it has to be, is this thing accelerating? Okay, is this object accelerating? Right? No, this sign is not. It should be a stationary sign. So F net y then, right? It's not accelerating. What else is 0? Well, it's not accelerating because F net y is 0, right? Now, what is F net y? We're going to rewrite F net y. What is that? It's the sum of all the y forces, okay? So Fty plus Fg, okay? I would add in Fny, but as we can kind of see, it's 0, so I'm just kind of going to cut out that step this time, equals 0 newtons, right? Fty plus Fg equals 0. Like I said here in my VAD, okay? Like I said here. This is saying the exact same thing as this is saying. Okay, so then, manipulating this, Fg, right, equals negative Fty. Remember, what are we looking for here? We're looking for the max sine weight. Max sine weight is just Fg. So if Fg equals negative Fty, then all we have to do is figure out Fty, and we know the maximum Fg essentially, right? But what is Fty, right? Again, looking here, does this say something that you know to be true, right? Does always interrogate your kind of process as you go along. Fg, is it equal but opposite to Fty? Yeah, absolutely, right? It's down just as much as Fty is up, equal in magnitude but opposite in direction. Otherwise, it would be accelerating. So coming back here, Fty, okay, would be opposite to the 25 degrees. We know Ft, right? They told us Ft equals 2.5 times 10 to the 3 newtons. That's the tensile strength of the chain. So we have hypotenuse. We want opposite. So right? SOH, sine equals opposite over hypotenuse. So sine of 25 degrees equals opposite Fty over hypotenuse Ft. Okay, so that means Fty, so Fg equals negative, Fty equals negative. Fty is just Ft times the sine of 25 degrees, which means Fg also equals that, right? Fg equals negative Ft being 2.5 times 10 to the third power newtons, okay, times the sine of 25 degrees, and we get that the weight, okay, the max weight, the weight where if we had any more mass, if it was any heavier, the tensile strength would be exceeded and the chain would break. We have that Fg, the maximum would be negative 1056.5457, just keeping some extra sig digs in case I need them later. Newtons. Now that negative, what does that mean, right? Really, I should have defined up here, right? But I was defining, since I made FTY positive, right? That means down would be negative because FTY was up. Okay, so when I get that negative, it means that I'm down. So realistically, the maximum weight, since weight is a force and force is a vector, it needs a direction. Okay, it'll always be the same if you're talking about the force of gravity, but 1.1 times 10 to the third, just doing 3 sig digs, so 1, 2, 3. Sorry, 2 sig digs, because that's what I was given, times 10 to the 3 newtons, and we'll say down for now. In chapter 4, we'll rethink that idea of down. For now, we can just say down. Okay. Perfect, that's it. We found the max weight that that chain could support. But what about the max, the min strength of the supporting bar? Okay, so we're saying then, if the tensile strength is going to be that much, so if it's going to be pulling with that tension, how strong does the normal force need to be for this bar to not completely crumple, right? Because it is pulling this way, so it is squishing in on that bar. That bar is having to push back. At a certain point, anything will break, right? The materials could break down. So we're going to try and figure out how strong does that bar need to be. Again, these are the kinds of calculations that people that work with materials like this all the time really do, okay? This is huge in engineering, huge in all kinds of fields. So F net x equals 0 newtons. How did I know that? All right, take a second to answer that for yourself. How did I know that? How do I know that F net x is 0? And it's because the object is not accelerating, right? So F net x is just the sum of all x components. So Ftx plus Fn equals 0 newtons. Okay. And again, let's be careful here. Let's remind ourselves of our sign convention. We're going to say that to the left is negative, to the right is positive. So we're expecting a negative Fn, right? We should be getting that. It's a good way to check your work. Ask yourself what you're expecting, and then if you get it, you're feeling better. If you don't get it, ask yourself if something went wrong. Okay, so then Fn equals negative Ftx, right? That's just me subtracting Ftx from both sides. Okay, that makes sense because they have to be the same size but in opposite directions. So if the normal force equals the negative x component of the tension force, what is Ftx? Let's go back to our triangle here. So for Ftx, that is the adjacent side. So cos of 25 equals adjacent Ftx over hypotenuse Ft. And so Ftx equals cos 25 times Ft. Okay. So then the normal force equals negative Ft cos of 25 degrees, which equals negative 2.5 times 10 to the 3, I should say. 2.5 times 10 to the 3 newtons times cos of 25 degrees. And so the normal force that I'm getting is negative 2,265.7695 newtons. All right, what does that negative mean? Is that a good thing that we got a negative, right? Look at the diagram and decide. Yeah, you bet that's a good thing we got a negative. We said this way was positive. We knew our normal force had to be that way. We just were trying to figure out how big it had to be. So it's a good thing we got that negative. We would say that the normal force equals, I guess, based on the diagram, let's just call it left. We could also say 180 degrees, but I don't feel like being that fancy right now. Times 10 to the 3 newtons to the left. Okay, a bit of an extension question if you want to try this one on your own. Figure out maybe what would be the mass. What would be the max mass? Because this is the maximum weight. So what would be the maximum mass? Okay, try that on your own. I'll give you the answer if you want. So the max mass that I calculated when I did it was, I'll give you the unrounded version. So not to 2 sig digs. You can put it to 2 sig digs yourself. That's what I got. So try that on your own. See if you can figure out how I got that.
Okay, so now a slightly different hanging sign example. Just different in the setup, really not different in the approach we're going to take at all, right? It's still the same idea. All the forces need to add up to 0, otherwise this thing is going to be accelerating, right? F net must be 0 so that A can be 0. Okay, so here, what is the tension in each rope if the sign's mass is 150 kilograms? So they've drawn for us 2 of the forces here, okay? If you're a little unsure of what this means, there's a roof here, basically, right? Probably seen a sign like that, okay? Those lines, by the way, those kind of horizontal lines, those are often used in physics or engineering diagrams to kind of represent just a fixed surface. Okay, so in this case, a roof. Okay, so those ropes are attached to some roof there, holding the sign up. Now, they've drawn 2 of the signs here, 2 of the forces in for us. They've drawn FA and FB, which is in the tension along the rope, but looking at those forces, is something missing, right? So yeah, we can kind of conclude that, of course, this thing has a mass, so it must have a gravity, but you can also conclude that even just based on Newton's first law, right, FA plus FB, right now, the way FA is and the way FB is, they might cancel each other out side to side, but they don't cancel each other up and down. Cancel each other out up and down, right? FA is kind of up, FB is kind of up. So looking at this sign right now, it should be accelerating the way we've got to draw on the forces. So we must be missing a force. And of course, that force is the force of gravity, or the weight, okay? Now, I've drawn it roughly as big as I think it should be because it needs to cancel out A's upness and B's upness with its downness, okay? So there's our representational. Let's do our free body diagram. Okay, so on our free body diagram, we have, we simplify it all down to kind of one point that represents our sign there, and it has a gravitational force, like we said, down, but it also feels FA, or I guess that's FB, okay, and it feels FA. Just going to move my label. Okay, so now let's move on to our free body diagram here, okay, which again is just a way of simplifying it all down. So we have our sign represented by that point there. We have the force of gravity down. Okay, and then we have the force in rope B up at that angle there. Right, and we have the force in rope A off at actually the same angle, just in the other direction, right? Okay, let's just take a second and look at these in terms of their components. So FB, right, is not entirely in the X and entirely in the Y, so it has an X component that looks like that. That's FBX, okay? But it also has a Y component that looks like that. That's FBY. And the same actually goes for FA, right? Here's FAX, and here's FAY. So like we were saying, right, we know that the tension in A and the tension in B, the force in A and the force in B must be strong enough in the y-axis together to perfectly cancel out with the gravitational force down, okay? Let's also think about what that means for FAX and FBX, right? Well, this thing is not accelerating side to side either, so the net force there must also be 0. So however much FAX is pulling to the left, FBX must be pulling back to the right. So that overall the net force is 0. Okay, there's our free body. Let's do our vector addition diagram, our VAD. Okay, so which forces do we have going on here? We have FA. We have FA going like this, off at 27.4 degrees. That is FA, right? We have FB coming back, and we know, right? Actually, I'm going to draw. Stop me in your head, say stop out loud when I'm good. Okay, and hopefully you're saying stop, right? Because I know that the leftness of FA needs to cancel with the rightness of FB. Okay, and then my force of gravity again. Is this thing accelerating? No, not in the X, not in the Y, not overall. So it can't have any net force. So the gravity takes me right back to where I started, so that if I were to draw it, I would have no component at all, right? And again, FAX would be here, FAY would be here, FBY could be here, FBX could be here, or here and here, so that we can use the angles. Let's just go back and actually add that angle in here over to our free body, just so we can quickly reference it if we need it. 27.4 degrees and 27.4 degrees. Okay, I'm just going to point something out here that will be useful to us in a second. Okay,
Let's actually take a look. FA and FB. What do you think? Let's not worry about direction, but in just size. How do you think they compare to each other? Okay. We have the same angle here, and we know that however hard A is pulling to the left, B must be pulling to the right. So if we have the same angle that they're pulling at, right, and however hard A is pulling to the left, B must be pulling to the right, that means FA must be pulling just as hard as FB, right? They're pulling equally. Otherwise, when we did cos theta to get the x component, for example, we get a bigger number or a smaller number if the angle wasn't the same, or sorry, if the angle was the same and FA was different. So I'm going to show something you might not have seen before. If you've taken Math 20, you have. It's no big deal. It's the absolute value sign, or in physics, we usually say it means, sorry, we usually say it means the magnitude, okay? So all that is that the magnitude of FA, okay, or absolute value, as you've probably seen it in math, right? In absolute value, what does that mean? It just means get rid of the negative if there's a negative, pretty much, right? It means how big is it? Don't worry about if it's negative or positive. So like the absolute value of -1 is 1. The absolute value of +1 is also 1, right? The absolute value of -5 is 5. The absolute value of -6 is 6, and the absolute value of +6 is 6. Basically saying how far is it from 0. But the magnitude of FA, right, just meaning how big it is, must be equal to the magnitude of FB, okay? So let's just, since they're kind of the same, I'm just going to give them the same name. I'm going to call it the magnitude of F, okay? That's going to come important in a sec here. I just wanted to get that out of the way while we were kind of here talking about FA and FB. But back to business as usual, okay? You can kind of, we'll store that in our back pocket. It's just something I wanted to point out while we were here. Let's go. How are we going to figure out the tension in each rope if the sign's mass is 150 kilograms? Let's also just remind ourselves, Fg, right, is always equal to mg, the mass times the acceleration due to gravity. Because every F is an ma, gravitational F is an m times a due to gravity, or g. Okay, so if we want to know the tension in each rope, let's think about it. Well, if I look at the x-axis, that's not going to be that useful to me, right? Because I don't know anything about this. G doesn't contribute anything. Fg doesn't contribute anything. Okay. Yeah, this must be equal to this, but I don't know anything about any of this stuff. I don't know the tension in A. I don't know the tension in B. So that's kind of useless. However, what if I look in the y-axis and say that, okay, F net y equals 0, of course, because it's not accelerating. And what is F net y? Well, it's Fg plus the y component of A, so Fay plus the y component of B, so Fby. And that equals 0, because F net y equals 0. Okay, we know Fg is mg, so essentially we have it, right? Because we know m and we know g, so mg plus Fay plus Fby equals 0. So I want you to notice something here. Fay plus Fby. How do Fay and Fby compare? Well, like we said before, the size of Fa is the same as the size of Fb. So we're saying, let's just call that size F for now, right? So the y component of Fa is not only the same size as the y component of Fb, it's actually in the exact same direction, right? It's up. Look at it here on our diagram. You compare Fay to Fby. They're actually the exact same vector. So if we call that size, let's just say Fay equals Fby, right, equals Fy, just for the sake of not assigning it to one, so Fay equals Fby, just equals Fy, okay? So we're saying this size of this vector, we're going to denote that as Fy. Well then, we have mg plus Fy plus Fy, because they're the exact same thing, they are equal to 0. So then that means 2mg plus, 2Fy equals 0. Okay. And so F2Fy equals negative mg. That's me subtracting mg from both sides to get Fy by itself. Okay, divide by 2, and look at that. Fy, which is the size of both Fay and Fby, equals negative mg over 2. Now, what did I say about when we're going, does this make sense? Okay, what is this saying? It's saying that each one is supporting the weight
divided by 2, or half of the weight, half of the force of gravity. Each rope is supporting in the y-axis half of the weight. Well, that totally makes sense, right? We've got two things contributing the same amount in the y-axis, so yeah, they're each going to be responsible for holding up half of this weight. Okay, so good. That does totally make sense. Okay, and so I got that Fy equals negative mg over 2, which equals negative, the mass of the sign was given as 150 kilograms. Okay, again, sorry, we should assign, we're plugging in now, so we should assign some directions. Let's say up is positive, positive, negative, negative. Okay, so if we're saying down is negative, then G is down, and that's negative 9.81 meters per second squared over 2. That's half of the weight. And so Fy is equal to, I'm getting 1,471.5 newtons. Which way? Which way does this force have to be up? For each one, it's up, right? So this is what each rope is supporting in the y-axis, okay? So again, Fy is the same as Fay and the same as Fby. I just kind of did this to say that let's just call it F, so that we're not denoting it to A or B, even though they're going to be the same number. So Fy, which means Fa is supporting that much and Fb is supporting that much in the y-axis. So Fay equals 1,471.5 newtons, and Fby equals 1,471.5 newtons, both up. Okay, but they didn't ask for the y component of the tension, they wanted the total tension. Okay, so how can I turn that Fby and Fay into just Fa and Fb? Well, we need to go back to our triangle here, right? You can see that Fby, right, the y component of Fb is the opposite side to the angle, and Fb is the hypotenuse. So I want the hypotenuse, I actually have the opposite here. So in this case, sine of 27.4 degrees equals opposite Fby over Fb. Okay, it's a little different than usual. Usually we're looking for the y component. This time we have the y component. So now multiply both sides by Fb. Okay, multiply by Fb, what we're looking for. And then we'll have Fb, tension in B, times the sine of 27.4 degrees is equal to Fby. It's okay that we're not done. We don't always finish in one step, right? So now divide both sides by the sine of 27.4 degrees. And lo and behold, we have, okay, Fb, right? I'm just going to bring this back down, actually, just doing it up here so you can see the triangle as I solved it. Okay, so this Fb is equal to this. Now, looking at Fa, you can try solving it on your own, or you can kind of take my word for it that it's going to end up being the same thing. You know what? You shouldn't take my word for it. Go prove it on your own. Go see that you end up getting the same thing, and come back. Okay, Fay equals 1,471.5 newtons. So then Fa, like we just showed, is equal to Fay with sine of 27.4 degrees, which equals, if Fay is 1,471.5 newtons divided by sine 27.4 degrees, we get 1,598.762 newtons. Okay, and that is for Fa. That is also for Fb. I'll let you try it for both if you don't believe me. Okay, which you shouldn't take my word for it. So if it makes sense, why it'll be the same for both, don't bother. But if it doesn't, try it out and make sure you do get the same thing. Okay. The only thing is, Fa and Fb are both vectors, so we should definitely be giving an angle. So Fa, actually Fb, is a little more straightforward. It's going to have, putting this into 3 sig digs, we would have 1.60 times 10 to the third power newtons at what angle? Well, we're going to use our Cartesian kind of method here, right? So our Cartesian method would be, this is 0, okay, and we make the angle as we go this way. So for B, it's pretty straightforward. We start at 0, we went to 27.4 degrees. So that would be the angle at which FB is acting. It's acting at 27.4 degrees. Boom. There's the answer there. FA is similar, but, okay, if I went all the way, if I went from here all the way, I would have gone 180 degrees, but I didn't, right? I went and I stopped short, so I went 180 minus 27.4 degrees, which is 152.6 degrees. So when I go to record the direction of FA, because it is a vector, it needs a direction, I would put 152.6 degrees. And there we go. That's the force of A and the force of B, the tension in each room. Now this is definitely a question where if we were in class, I would have told you to do this as a whiteboard problem, okay? So I would suggest now pausing the video, try it out, okay? I'm going to solve it, but this is when I'd like you to try your own, and then if you get an answer, skip to the end, see if you got it right. If you don't get an answer, or if you get stuck along the way somewhere, maybe just skip ahead a few minutes, see if you can, if you need to push in the right direction, okay? So this one asks us, what is the tension in each rope if the sign's mass is 150 kilograms? Very similar to the last one. Maybe the forces are a bit different, but the same exact kind of idea, right? So they're missing a force here. What are they missing? Well, we've got some upness that's not canceled by this guy, right? Of course, we know they're missing gravity. So we draw our free body diagram. We have our sign with a force of gravity acting downwards, a force of tension, 1, Ft1 they're calling it, okay, acting that way. So Ft1, and then Ft2 acts exactly this way. So think in your mind, when should I stop? Right about there, right? Because that way, the rightness of Ft1 will get canceled out by Ft2, because as we know, everything must cancel out. There can't be a net force where this will be accelerating. Okay, let's just, for a second, think about angles here, okay? They were a little tricky. They gave us the angle between the roof here and the cord over here on this end. That's not where our tension is, right? Our tension is happening, that's not how we would direct a vector, right? We wouldn't say it from the end of the vector. We always direct the vector from the beginning. So when I'm looking at it, I'm thinking, okay, let's split this into X and Y components. So the Y component of Ft1, right, you can picture it, is up, of course, okay? The X component is to the right, of course, right, because this thing is going uppy righty. So if this angle here is 40 degrees, right, then, well, so is that angle there. Now, if this is 90, and that's 40, and a triangle adds up to 180, right, then this is 180 minus 90 is 90, minus that 40, making this angle here 50 degrees, okay? Ft1y, right, and there's Ft1x, and this angle again is 50 degrees. Let's look at our VADs. So VAD, vector addition diagram, where we have to end up, we have to end up back at 0, right? So we've got, doesn't matter which order you draw them, right? Ft1, okay? Then we've got our force of gravity, which we know should stop right when it's just as big as the upness of Ft1. Aha, there we go. Because Ft2 doesn't have a y component, right? So those have to cancel each other out in the y. And then what's going to do the job of canceling out our rightness from Ft1? Well, the leftness of Ft2. Okay, so that overall, no net force because the sign is not accelerating. So there is no net force for sure. Okay. Let's do our XVAD. Again, these are not mandatory, but they do help to kind of visualize, I find, what's really going on. Why are we doing what we're doing? Why are we separating into components? So Ft1 X looks like that, right, from our diagram. And why is it not accelerating off to the right? Because Ft2X is pulling it back just as hard. If we do it in the y-axis, right, there's definitely gravity because this thing has some mass, okay, 150 kilograms of it. So there's definitely some gravity down. Fg, well, that's not very straight, oh well. Okay, why is it not falling though? Because there's a tension, Ft1y, pulling it right back up. Okay, so the mass of this thing is 150 kilograms. And don't forget, every F is an ma, so every Fg is a mass times acceleration due to gravity, right? Every force is a mass times an acceleration, so the force of gravity is mass times gravitational acceleration. Fg equals mg. So, when I'm approaching something like this, right, I'm thinking, okay, what do I know? Can I actually find a force right off the bat, right? Any of them? Well, yeah, I can find Fg right off the bat, right, which is a y force. So since I can find that right off the bat, it's probably the force I'm going to want to end up working in. Okay, or the axis, sorry, the y-axis is probably where I'm going to want to start working in, because I can get that, which means, hey, hang on, if I look at my VAD and the y, if I know Fg, right, well, I know Ft1y is equal but opposite, and the math will show us that as well. So let's start in the y-axis. F net y equals 0, Fg plus Ft1y equals 0, and like we just said, that means Ft1y equals negative Fg. Okay, so I could solve for Ft1y here and then go to my triangle and figure out Ft, or I could kind of just do that right now and say, okay, but what is Ft1y in terms of Ft? Well, if I'm Ft1y to this angle, I'm adjacent, and Ft1 would be hypotenuse, so then that means cos 50 equals adjacent, Ft1y, over Ft1, okay? So then Ft1y equals Ft1 cos 50. Doing that because now when I go back down here, I'll be able to just solve for Ft1 right away. Alternatively, I could have found Ft1y with this expression here, then gone up to this guy and then figured out Ft1 after. I'm just kind of compressing two steps into one here. So Ft1y is Ft1, the overall tension, times cos of 50 degrees, and that's equal to negative Fg, which we know Fg is mg. Okay, I'm about to start plugging in, so I need to define directions to be careful here. Okay, we'll say up is positive, down is negative, right is positive, left is negative. Okay, and so if that equals negative mg, and I want Ft1, let's go ahead and divide both sides by cos 50. Then Ft1 equals negative mg over cos of 50 degrees. Okay, great. So now I know all that stuff. So that means I know Ft1 essentially, right? If I could just plug it in the calculator and be careful with my signs. So Ft1 equals negative. The mass of the sign that's being supported is 150 kilograms. Gravity, I said down was going to be negative, so acceleration due to gravity would be negative, because that's always down, of course, right? Drop something, it falls down, divided by cos of 50 degrees. Okay. So plug that all in your calculator, you should get that Ft1 equals a negative. Negative is a positive. Well, that's good because the tension should be up, right? It's fighting gravity here. 2289.25 newtons. All right, so that means this is one of our required, right? This is one of the required of the problem. We wanted the tension in each rope, so Ft1 is something we wanted. And so we'll give our proper sig dig answer with the direction. It's 2.293 sig digs times 10 to the power of 3 newtons. What's its direction? Well, it'll be at that, it'll be from our, if we're using Cartesian coordinates, right, from our 0, which would be here, it's not quite, it's not going to be 50, it's going to be 90 minus 50, right? So that angle there is 50. If this is 50, right, like we said, well, this would be 90 minus 50, or 40. So that's the direction of Ft1, 40 degrees. Okay, what about Ft2? Now, since we know Ft1, okay, we use that to figure out Ft2. Let's look at our VADs in the X, right? This is kind of what I mean. This is a mathematical, it's a visual representation of a mathematical equation, I guess, right? They must be equal and opposite. Otherwise, there would be a net force in the x-axis. And so we can kind of say that realistically, you could jump straight to what I just said, and that ft2 equals negative ft1x, but let's just start here just in case. Okay, f net x equals 0. What's f net x? Well, it's ft2, that's in the x-axis. It's entirely in the x-axis, right? It doesn't have a y component, plus ft1x, that equals 0. So ft2, like we said, would be negative, equal but opposite to ft1x, right? Just like we said in our VAD in the x-axis. Okay, so what is ft1x? Well, sine of 50 degrees equals opposite over hypotenuse. Opposite over hypotenuse. Now we actually have the hypotenuse, so sine equals opposite over hypotenuse. So sine of 50 degrees would be ft1x over ft1. So then ft1x would be ft times sine of 50 degrees. Okay? So again, not forgetting what our negatives and our positives mean. Which way is ft1? Which way is it? It's to the right. So that can be a positive vector, right? We'll say we define right to be positive. So we're hoping to get a negative here. If we don't, that would be bad news, right? That wouldn't make sense. Equals negative, what's ft1? We just found it to be 2289.25 newtons. Good thing I kept extra sig dig because I had to use it again later. Times the sine of 50 degrees. And so ft2 would be, I'm getting, okay, negative 1,753.67 newtons. Good, I did get a negative. I was expecting one, right? It needed to be the left. It needed to be to the left to cancel out with the rightness of ft1. Okay, so all that's left to do now is direction and sig digs. So to 3 sig digs, that would be 1.75, right? Not 175, that's not the same number, right? 1.75 times 10 to the power of 3. Okay, I need to move that decimal 3 times. 1.75 to 10 to the power of 3 newtons. At which angle? Which way is it going? Okay, so careful, it's not 0 degrees, right? 0 degrees would be that way. ft1x is at 0 degrees. ft2 is the opposite way. It's at 180 degrees, right? If I draw it all the way around. Okay, at 180 degrees. So which do you need to use a stronger material for? The rope doing ft2 or the rope carrying ft1? Well, ft1 is going to need a stronger material, right? Because it's going to have to take a greater force. Okay, last thing for this section, for this topic of this week. So example 11 is when we're pulling at an angle. Okay, now this looks a little bit different than the sine questions we've been doing, but realistically it's kind of not. I mean, in terms of our approach anyway. It's going to still just basically end up being f net equals 0, because this is all about Newton's first law type stuff. So if this person requires 100 newtons of force to maintain a constant speed, what is the force of friction? Okay, so again, what does that mean? Constant speed. This is where students trip up. They think, oh, it's moving. It doesn't. It does have a net force. It is accelerating. No, moving does not mean accelerating, right? Constant speed, A equals 0 meters per second squared. And if A is 0, well, why is A 0? Because F net is 0, right? A net force causes an acceleration. So constant speed right away, this thing is not accelerating. But what is the force of friction? Okay, let's first not get ahead of ourselves. Let's draw in some forces. So they're pulling with a force of 100 newtons. They're pulling with a force of, let's call that, we'll call it a tension force because it would be to the box. It would feel it as a tension through the rope. 100 newtons. Okay, what else is this box feeling, or this weight? Well, it's got mass, so it's got a force of gravity, right, a weight. Now, why isn't it falling through the floor, right? Because, now be careful, there's a couple reasons here, okay? It's not falling through the floor, yes, because there's some normal force supporting it, but should I make the normal force as big as the force of gravity? I want you to think about that, okay? If I do, well then what about this here? what about the y component of that Ft? Draw the x component in so it doesn't look weird. But what about that? That's part of this, right? So think about it. I'm lifting it up a little bit. So the normal force actually has to do a little bit less work than it usually would to fight against gravity, right? So we'll draw that a little bit smaller. Otherwise, it would actually be accelerating up, right? Because I would have bigger up forces than I do down forces, okay? So if you can kind of think about this, imagine you're holding something above your head, right? You're supplying the normal force. If someone is above you kind of pulling up on it a bit, you don't have to push up as hard. You don't have to supply as big of a normal force, right? Think of like if you're passing something up to someone while you're moving your friend into their house or whatever, right? You're holding it up above you. When they start to grab it, you don't have to hold on as hard. The normal force that you have to supply gets smaller because some of that force of gravity that you were originally supporting against is now being alleviated, being relieved by that upward component of them pulling up the tension there. Okay, so have we forgotten anything? Yes, we have, because this thing would be accelerating, right? Which axis would it be accelerating? You're looking in there. So we just made a big deal about talking about how the y components, right, all cancel out. What about the other axis? Does it look to you like the x-axis is being canceled out? Nope, right? We're forgetting something. Ftx is this way. This thing is accelerating the way I've got it drawn, but we know it's not, so we must be missing a force. And aha, the whole point of this question, the friction, right? Ff. Okay, so there's some friction backwards. Okay, that's a bit of a jumbled mess, so let's put it a little bit more simply on our free body diagram. Okay, we have the force of gravity straight down. Okay, we have the normal force up, but again, it's not as big as the entire force of gravity because it doesn't need to be. Why doesn't it need to be? Because we're alleviating some of that with an upward tension, or a partially upward tension. Tension isn't completely upward, but it does have an upward component. Okay, now that would also be causing, looking at this free body right now, it would be accelerating because there's the rightness of the tension, unless there's some leftness in the form of friction. Okay, let's just visualize our components here. We have Ftx and we have Fty. Okay, great. And once again, this angle here, they've told us, is 40 degrees. So looking at this now, we can kind of see, okay, yeah, this plus this must equal, in the opposite direction, this force of gravity. Okay, let's draw our VAD to see that in action a bit better. Okay, so on our VAD, let's start with the force of tension. It really doesn't matter which one we start with though. Force of tension. Okay, and then we have a force normal up, a normal force up. Then we have a force of friction that just cancels out the rightness of the tension. Okay, and now all this upness is there. What's getting rid of it? Yes, the downness of gravity, right? Okay, so there we go. We end up back at 0. So this is an important note. Fg is not always equal and opposite to Fn. Okay, we touched on that earlier, but now it's back in a big way, right? Fg is not always equal and opposite to the normal force. Don't always assume that. Okay. Normal force does not have to do all the work in the y-axis. So let's make that a little bit even clearer with a VAD. Well, first in the x, and then we'll look in the y. What's going on in the x? We have Ftx, right? And as we said, why is it not accelerating to the right? Because the force of friction is pulling it right on back. Okay, so that it doesn't accelerate. What's going on in the y? Just to save room, I'll pop over here. Okay, now this is where things are a little more interesting. Maybe we haven't seen this exact thing before. Well, we have the normal force. We have the normal force. We have Fty. And then why is it not flying up off the ground? Why is it not accelerating up? Because of the force of gravity, right? So that overall there's no net force. F net is 0 in both the x and in the y-axis. Okay, so what is the force of friction then? Well, let's take a look. F which axis is more interesting to me here to figure out the force of friction? Is the y going to do me anything? Well, no, because in the y-axis, the force of friction is 0, right? So that's really not too helpful. However, in the x-axis, we know that, again, F net x equals 0, right? Okay, so what's going on in the x-axis? Let's go over to our VAD. In the x-axis, we know that FTX, right, plus FF equals 0. Okay, before we go any further, I'm going to define my directions. This way, right will be positive, this will be negative, up will be positive, down will be negative. FTX plus FF equals 0. What are we looking for? What's the point of this question, right? We wanted to find the force of friction. Okay, the force of friction. So subtract FTX from both sides, subtract FTX from both sides, and we have that. Okay, the force of friction is equal to negative the force of tension, the x. In other words, equal in size, but opposite in direction. Hey, that's exactly what we said, right? For this to not be accelerating, FTX has to be just as big to the right as FF is to the left. So the force of friction is equal to negative FTX, which equals negative FT, oops, getting ahead of myself. Okay, what is FTX, right? Go back to our diagram here. Well, it's adjacent to FT's hypotenuse, right? So we know FT, it's 100 newtons. So it's adjacent and hypotenuse, that's cos, right? Cos of 40 equals adjacent FTX over hypotenuse FT. So FTX equals FT times cos 40, right? Just multiplying both sides by FT. Okay, so equals negative FT cos 40 degrees, and the force of friction is therefore equal to negative 100 newtons times the cosine of 40 degrees, giving us that the force of friction is, okay, we're expecting a negative, right, because force of friction is to the left, so I got negative 76.604 newtons. That's good, I wanted a negative, right? The math will have your back, but you also don't ever want to be a robot, right? Think about what your answer means. Think about what you're getting along the way, and if that makes sense, if it agrees with what you know to be true based on the physics. So the force of friction then is equal to, let's go ahead and give that negative a direction, 76.6 newtons. I would say, right, it's this way, okay? It's perfectly that way, so that's 180 degrees. Okay, so that wraps up, kind of wraps up 3.1, 3.2. That's this week's sort of topic. So the extra practice assignments, the ones that you normally would be just kind of given in class, you should be able to do all of the questions in there now. Okay, so those are good for the practice, and then also the Google Forms, that is your kind of hand-in assignment for this whole thing. So if you have any questions, feel free to reach out to either myself or Mrs. Ellis.